So in question 424, what we've got is we're told that the weight of an object is the same on two planets. And we're told that the mass of one planet is 60% that of planet B, and it wants us to find the ratio of the two planets. So pretty much what we've got is initially, let's say, someone took an object to planet A. So here's planet A. And planet A, I'll say, has a radius of RA and has a mass of MA. So what they did was they took this object there and they weighed it. So here's the object. So I'll say this is an object of mass M, little m. So this diagram is probably a bit out of scale because this would, if this is a planet, that would be an absolutely enormous object to take there. So obviously, yes, so this is a bit out of scale, but yes. Just assume that is a small object I've just drawn hopelessly out of scale. But anyway, so they took this object to planet A and they weighed it. So in other words, they measured what the gravitational force was between this object and that planet. So that's what we mean by weight. The weight of an object on Earth, say, so the weight of this calculator, is the gravitational force that acts between the calculator and the Earth. But then what this person did was they then took this same object to another planet, which is planet B, which presumably has a different radius. So I'll call the radius of this one RB, and it has a mass of MB. So they took this object, the same object, and they took it to this planet B. And they weighed it again. That is, they again measured what the gravitational force was between that object and planet B. And they came up with the same number. So armed with that knowledge, what the question is asking us to do is to figure out, given that we know something about how the masses of these two planets are related, is to come up with a number for the ratio of the radiuses of the two planets. That is, one radius divided by the other. Now, we have a formula, that's Newton's universal law of gravitation, which we could use to figure out what the weight or what the gravitational force was between this object and this planet here, and similarly here. So what I reckon would be probably a good thing to do would be to use this equation here to figure out what the weight is, to at least obtain an expression for the weight of this object on planet A and for the weight of the object on planet B, because according to the question, those two weights are equal. So we can probably then get an equation which we could solve for what the question is asking for us for. So let's say that the weight of object on planet A well, that's going to be, let me call it WA, and that's going to be equal to the product of the masses of these two objects, so the product of the mass of the planet and the mass of the object, divided by the distance between their centres squared. Now in this case, well, usually because planets are so much bigger than any object sitting on them, the distance between the centres of these objects is probably going to be approximately equal to the radius of the object. So we should say, assume object is small compared with the planet. If we couldn't make that assumption, then this distance squared wouldn't be quite right, because we would have to also include the radius of the object, assuming it was spherical. But if the object is small in relation to the planet, then the distance between those two objects is just pretty much equal to the radius of the planet. And then we should probably also remember that we need to multiply this by Newton's universal gravitation constant, which is that big G. So when we take it to planet B, we're going to find the very similar equations. So the weight of object on planet on planet B is going to be given by an expression which is exactly the same, but with the relevant quantities for planet B instead of A. Now the question tells us that whatever these weights are, they have to be equal. So we can set this expression equal to this one. So all this junk here has to be equal to all this junk here. So since the weights are equal, we find that G times this product of masses divided by the radius of planet A squared, it's got to be equal to the same thing for planet B. And what we see here is that both sides have some identical factors. So both, for example, have this big G, so we could just divide both sides by big G, and these would go away. Both sides also have a factor of the mass of the object, so we could divide both sides by this m, and these would also go away. And what we'd be left with is just this. Now what we want to know is RA divided by RB. So if we now multiply both sides of this equation by RA squared, see this is this looks a bit bad because we've got RA squared in the denominator and we actually want it in the numerator and we want it divided by RB squared. So let's multiply both sides of this equation by RA squared. So if we do that, we'll end up with just the mass of planet A is equal to the mass of planet B divided by the radius of planet B squared times by the radius of planet A squared. Now we almost have RA squared on RB squared, but it's being multiplied by this pesky mass of planet B. So if we just multiply both sides of this equation by the mass of planet B, then we get that the mass of planet A divided by the mass of planet B is equal to RA squared divided by RB squared. And when we have a fraction in which the numerator and the denominator are both being squared, we can introduce a set of brackets and just square the whole fraction in one go. So we could equally write this as a fraction, so the ratio of the two radiuses in brackets with a little square, like that. And then if we sort of go up to here, what we can do then is we want to get rid of this square, because what we want is the ratio of the two radiuses, not the square of the ratio of the radiuses. So we can just take the square root of both sides of this equation to kill off that square there. And so what we arrive at is that the ratio of these two radiuses has got to be equal to the square root of the ratio of the masses. So in order to know the ratio of these radiuses, we need to know what the ratio of the masses is. But fortunately, the question tells us that the mass of planet A is only 60% that of planet B. So we know that whatever this mass of planet A is, it's only 60% of this one. This means that the mass of planet A is just equal to 0.6 times the mass of planet B. So writing this is exactly the same thing as saying that the mass of planet A is 60% the mass of planet B. And if we now just divide both sides by this mass of planet B, what we end up with is that the mass of planet A divided by the mass of planet B is just equal to 0.6. And so if we now replace this MA divided by MB with what it is, which is 0.6, we find that the ratio of the two radii is just equal to the square root of 0.6. And that is equal to, 0.775 or thereabouts.